Hi everyone, welcome again to yet another session in which I'm going to explain how to find a solution for this type of second order ordinary differential equations using variation of parameters, okay, and subject to some initial conditions. All right, so the idea is pretty simple. So we need to assume a homogeneous ordinary differential equation. So we set the right hand side equal to 0 and we end up with 4y prime prime minus y is equal to 0. This is the assumed homogeneous equation. All right. So the auxiliary equation to this one will be 4 r squared minus 1. Be careful. The power of r, which is the characteristic variable that we're using, we will take the order of differentiation for y. So in this case, 4 r squared matches this double prime, and there isn't any single prime, so we can't write r here, but we just write 1 equal to 0. But if you look at this expression now, it's a quadratic thing, which is a difference of 2 squares. So factorizing this one from your metric knowledge, you will end up with 2r plus 1, and 2r minus 1 is equal to 0. Now, having factorized this characteristic equation or auxiliary equation, then you can clearly see that r is equal to plus or minus 1 over 2. Thus, one can now say, okay, the complementary solution for this problem would be C1 e to the power of half x plus C2 e to the power negative half x. The order doesn't matter, right? You can start off with a negative half to the power of x here. If you switch things around, the order doesn't matter, okay? So having found the complementary solution, we can now say, okay, we know the nature of the particular solution. So therefore, the particular solution takes this form: u1 y1 plus u2 y2, right? So we need now to determine u1, u2, because from these two we can match that y1 is equal to e to the half of x, which is exactly the function being multiplied by c1, and also we can match this side and say y2 is equal to this other piece, e to the power negative half of x. Where are we going? What do we intend to achieve at the end? Remember, an ordinary differential equation is the solution of an ordinary differential equation is a sum of a particular solution and a complementary solution. So we have found a complementary solution. From that complementary solution, then we said, the particular solution will take this form in which y1 and y2 are these two expressions down here. So we need to determine u1 and u2 in order for us to have a complete form for yp. So let's do that. So we know that, so now I need to explain something. Some people were just asking me now, the thing around the Wronskian. Okay, so the Wronskian, so before I write the formula for the Wronskian, I need you guys to appreciate that u1 prime, the derivative of this these are functions, right? These are functions, u1 and u2. So the derivative of the function u1 is equal to some Wronskian 1. If I'm going to I don't want to confuse people. So u1 is equal to minus y2 times f of x or g of x, the function g doesn't matter. What we are referring by f of x is that function on the far right side. So in this case, this is our f of x, all right? So that divided by the Wronskian. So I want to emphasize that right here, guys, we divide by the Wronskian alone. Let's not put the modulus, right? Let's not put the modulus for the Wronskian. You take the Wronskian as it is, which is the determinant of that matrix I will show you just now, and then place it here. And be careful, u1 prime, you put a negative y2 that, and u2 prime is calculated from y1 by f of x over the Wronskian. But before we calculate these two quantities, I want you guys to appreciate that these formulas are just the same. This expression that I have here is just the same, even if one has to say, okay? I'm just checking for comments there. Okay, cool. So some text can say the Wronskian 1 over the Wronskian. So these two are just the same. And I'll explain why. Because the Wronskian 1 is equal to the modulus of so remember, for the Wronskian W, it is y1, y2, y1 prime, y2 prime down here. So for this one, now it will be a 0, y2, I'm sure guys you are following, and this will be your f of x down here, and that will be y2 prime. Okay? So it's like you are replacing, I want to write the formula for the Wronskian without this 1. It takes y1, y2, y1 prime, y2 prime. So for you to find w1, if you don't want to use this form, you must use Wronskian 1 over the Wronskian. But Wronskian 1 is calculated from this determinant down here, where you replace your y1 with a 0 and your y1 prime with your f of x. All right? If you do that, then you will calculate the determinant of this. So you say this times that, you get should be, is this the other way around? y2 prime, that's okay. That's 0 minus y2 f of x. Okay, perfect. That's correct. So, okay, cool. So if we are going to simplify this, let's see what the determinant of this Wronskian 1 is going to be. 0 times that, it becomes 0 minus this times that. So you end up with minus y2 f of x all over. Okay, so Wronskian 1 is just this. Alright? So instead of writing Wronskian 1, look at this. We have the actual expression on top. So instead of using these fractions, Wronskian 1 over Wronskian, we just pick that. So these two are equivalent statements. So even here, you end up with Wronskian 2 over the Wronskian. So if you are going to work out what Wronskian 2 is, Wronskian 2 is equal to the determinant of, you put y1 this time, and y2 becomes 0, and this is y1 prime, and then this becomes your f of x. Alright? So if you do the determinant here, you will find that this times that, you end up with y1 f of x. Alright? Then this becomes minus a 0, so we don't write anything. So if you can see, this W2 is replaced by this, which is exactly the top quantity. So to make life easy for you guys, this form is equivalent to that. This form is equivalent to that. So to make life easy, forget about these fractions, Wronskian 1 over Wronskian, then Wronskian 2 over Wronskian. If you can recall that U1 prime is calculated from this and U2 prime is calculated from that, yeah, home and dry. It matches Wronskian 1 over Wronskian and Wronskian 2 over Wronskian. So with these two, we can work out U1 and U2, which is our main goal. So let's do that. So U1 prime is equal to, okay, we need the Wronskian before we calculate what U1 is. Let's do that. What is the Wronskian in our case? It takes Y1, Y2, Y1 prime, Y2 prime. Let's do that. So what is Y1? Is e to the power half of x. And what is Y2? Is e to the power minus half of x modulus. Then let's take the derivatives here. Derivative of that is half e to the power half x. Then this one takes minus half e to the power minus half x. Okay? So if I'm going to find the determinant this like that, then the powers will add, I'll get a 0, then I'll end up with a negative half. The formula says I should say minus. Then this times that, the powers will add and I'll get a 0. So e to the power 0 is a 1, I'll remain with a half. If I simplify this, I'll get negative 1. Alright? So now therefore, U1 prime is equal to minus, what is Y2? It's e to the power negative half x. That, I'm substituting this formula. So this is minus Y2 times f of x. F of x is that function that exists on the right hand side of our ODE, which is x e to the power of half of x. Right? Everything divided by, we take the Wronskian as it is, okay? And then let's divide here by the Wronskian as it is. Alright? So let's do that. So if we simplify here, the negative will cancel. This power will add up with that power, then I'll get a 0. E to the 0 is a 1, is a yes, and then 1 times x, I'll end up with an x. And this implies that U1 is equal to, because I need to integrate to reverse the differentiation, so this is the integral of x dx, okay, so which will give you x squared over 2. So now that I've found U1, I need to calculate U2 as well. So U2 prime is equal to, according to that formula, I need Y1, which is e to the power half of x from here, okay? And then what is f of x is that expression up there. It's x e to the power half of x as well. And then everything divided by the Wronskian, which is negative 1. So if we simplify this further, we will have this times that, which is, we add the powers and we end up with half of x plus half of x is a single x. So we end up with x e to the x. Then negative because of that. Alright? So now, for us to determine what U2 is, we need to integrate that function on the right hand side. So I need more space. Let me wrap this top part, but we'll leave our original ODE and the initial conditions. We will use these ones later to determine the constants. Alright? So U2 is equal to negative integral of x e to the power of x dx. Alright? So, this is integration. We use integration by parts. Alright? So, then we let one of these to be v. So, it's the integral of u dv, which will simplify to uv minus integral of u dv. V du, rather. V du. Alright? So we say let u be equal to x and dv be equal to e to the x. Then du is 1 and v is equal to the integral of this thing is e to the x. Therefore, u2 is equal to minus this integral. So let me put this big bracket. This negative is this one, and then I'm going to write uv. This times that, I'll have x e to the x minus integral of v e to the x times du, which is just 1 dx. So if I simplify this, I'll have x e to the x minus e to the power of x. So this is my u2. Now that I found u2, I can write the general solution as, remember it is yc plus yp, complementary solution plus a particular solution. So in this case, I will end up with, you remember the first solution was c1 e to the power of half x plus c2 e to the power minus half x, right? And then the other piece was saying u1 y1. So u1 is this x squared over 2, which is x squared over 2 times y1 e to the power half of x. Alright? And then the other piece was saying u2 y2. So u2 is this and y2 is that. So we end up with e to the minus half x multiplying what? Let me rub this piece. Okay. So end up with, this is y2 multiplying u2. u2 is x e to the x minus e to the x. Alright? Oh, okay, did I affect this negative? No. So I think I should be careful here. Negative that and positive that. Negative that and positive that. Yeah. Okay, mistakes are common in math. So, but you have to constantly check whatever you're doing. That's how I picked this error. So now, if I'm going to simplify this thing a little bit further, you end up with these pieces, they look fine, but maybe I can factor out e to the half x between this and that. So, or I can just leave it as it is, c1 e to the half of x plus c2 e to the negative half x plus x squared over 2 e to the half x, right? And then I want to remove brackets here. This times that, I will end up with minus x e to the minus half. So I have minus half x plus 1, which is just a half. So I'll end up with half x. Then this times that, I'll end up with e to the half x, because 1 minus half plus 1, then I'll end up with that. So this is my general solution to the ODE, because it has these constants. So now, in order for me to determine these values of these constants, I'm now going to use the initial conditions. So let's do that right here. So we are told that if we substitute 0 where there is x, the result should be 1. So let's do that. So y0 is equal to, we put a 0 here, you have e to the 0, which is 1. So we end up with c1. And this one, we end up with c2. And this one, if we put a 0, it becomes 0 because of x squared. And this one becomes 0. And this one becomes plus 1. Plus 1, the answer should be equal to 1 according to the initial condition. Then let's see, what is y prime? What is y prime? We need to differentiate this whole expression, and we need to differentiate that. Let's do that. So it's half c1 e to the half of x. I'm now here. And then minus half c2 e to the minus half of x. And then differentiation of these, it's a product here. It's a product uv, so I should just say plus. So I'll have e to the half of x. Then differentiation of this, it will be x, because it will be 2x, and then this 2 divided into 2, and then plus, I'll have x squared over 2. Differentiation of this will give me half e to the power of half x. Alright, I'm done with this product. Then I'm moving on to this one. Yet another product. So it's going to be minus x, right? Then differentiation of this one will give me half e to the power of half x. Alright? And then plus negative 1 by e to the power of half x. Okay? And then lastly, the last one is half e to the power of half x. Now, I have that derivative, so I use the initial condition again. 1 prime, 1 should give me 0. So let's do that. So we are going to put 1 where there is x. So we end up with half c1, and then e to the power of half minus half c2 e to the power minus half. Then this one becomes e to the power of half plus half. Half times half gives us a quarter, right? Quarter e to the power half, and then minus half e to the power of half, right? And then this one becomes minus e to the power of half, and then plus half e to the power of half. Alright, so this should be equal to a 0. Alright, so this should be equal to 0. Okay, so let's simplify further. Let's see where we can. So this e to the half, we'll cancel that e to the half, and this one will cancel that, so we are remaining with so we have two simultaneous equations now, so we can move the one that side and we end up with c1 plus c2 is equal to 0. And then look at this other piece, we have half of c1 minus half of c2, or we have e's there. We have e's. So we can factor out e to the power of half. And we will have half for this one, c1 minus half c2 plus 1/4 is equal to 0. Alright? So these are the two simultaneous equations we are supposed to solve. So we divide this second one by e, let's eliminate e, and multiply everything by 2. You end up by 4 rather. You end up with 2. So let's write the new, so it will be 2c1 if I divide by e to the half and multiply by 4. So I will be having 2c1 minus 2c2 plus 4 plus 1 rather is equal to 0. So I have these two simultaneous equations. So let me write them here and then try to solve them simultaneously. So C1 plus C2 is equal to 0, and 2C1 minus 2C2 is equal to minus 1. Alright, so I should eliminate 1. I multiply this one by 2 and subtract. So I'll have 2C1 plus 2C2 is equal to 0. And this one is 2C1 minus 2C2 is equal to minus 1. Let's subtract. This minus this 0. This minus this becomes 4. C2 is equal to 1. And C2 is equal to 1/4. So by equation 1, it means C1 is equal to minus quarter. So having found C1 and C2, you can now come to this general solution and replace the C1 with a negative quarter and the C2 with a positive 1/4. Okay? So someone would prefer to simplify it further by taking like terms, but this is basically the solution of this ODE, right? So the idea now would be now to group this and that, simplify it further, and possibly the ones with these two, they will simplify further. For this one, factor out xe to the half, trying to make the answer nice. But this is in a nutshell, this is the solution to this given ODE, subject to those initial conditions. I hope this helps. Okay, see you next time in the next video.